In this video, we're going to try to apply the alternating series test to help us determine whether a series converges. Now, you might notice from this left-hand side that I've crossed out or diverges here. And that's because the alternating series could only tell us whether a series converges. It can't tell us whether a series diverges, actually. So let's jump into this. So the first thing to do when considering an alternating series is we have to make sure it is indeed an alternating series. In this case, because we have that minus 1 to the n in the numerator, that minus 1 to the n is going to give us that flip-flop in sign of when n is 1, we have this as minus 1. When n is 2, we have positive 2. And this sequence of minus 1 to the n is always going to jump or oscillate between minus 1 and 1. So all alternations in sign are due to that term alone. Everything else in the series is positive. So if we take a look at the series positive terms that I just call Bn, we take everything else except the term that is responsible for the alternation in sign. So in this case, that would be a 1 over n squared plus 4. So that is our series function, or the part of our series function that is strictly positive. It's not causing any alternations in sign whatsoever. So for the alternating series test then, if these positive terms satisfy two criteria, then we can say that this series is convergent. So the first criteria that we use is we basically take the limit of those positive terms and we want to make sure it goes to 0. So let's first do that. So we take the limit as n goes to infinity of the positive terms. Again, that's the 1 over n squared plus 4. And when we look at this limit, well, in the denominator, we have an n squared. And since this limit is going towards infinity, this denominator is looking a whole lot like a super large number or infinity itself. And when we have a finite number, in this case, a 1 in the numerator, but finite nonetheless, divided by something that's growing and growing and growing, then this limit indeed is 0. So the first criteria for the alternating series test is satisfied. The second condition or criteria is that the terms in this sequence are decreasing. So let's take a look at that now. So there's a couple ways we could show that the terms in this sequence are decreasing. One way is we could do this algebraically, where we compare the next term in the sequence, and we want to show or make sure that the next term in the sequence, the bn plus 1, is less than or equal to the previous term. So we could show this more algebraically. Or if we define a function based off of our series positive terms here. So in this case, f of x could be a 1 over x squared plus 4. Again, basically where we're getting this function is by going back to the series positive terms and replacing those integer n's with a more real variable x. And then we can take the derivative and try to show that the derivative is always less than 0. To basically signify that this function is decreasing. So we could do either of those two approaches here. For some extra derivative practice, let's start with that. So again, we'll take our series function that has only positive terms, replace the n's by x's. So we have a 1 over x squared plus 4 as the function we're going to differentiate. I'm also just going to rewrite this algebraically in the following way, where you have x squared plus 4 raised to the minus first power. And the reason for doing that is basically just to do some derivatives. We can do chain rule as opposed to a quotient rule, but you could do quotient rule nonetheless if you'd like. So if we take the derivative now, because we have x squared plus 1 being raised to a power of minus 1, we can apply the power rule. So we bring that minus 1 in front. We multiply by what was originally there, except we subtract 1 from that power. So instead of a minus 1, we have a minus 2 now. And then we multiply by the derivative of what's inside. So the derivative of x squared plus 4, that is a 2x. So if we just do a little bit of algebra here, we can see that this derivative will turn into minus 2x all over quantity x squared plus 4 raised to the second power. So again, what we want to show this is that for all x values greater than 1, that this is indeed a negative quantity. So if we take a look at this denominator, for any x value greater than 1, and the reason why we care about x is greater than 1 is, well, that's where our series is starting off. So for x values greater than 1, this denominator is always going to be a positive number, because whatever is inside the parentheses, well, we're squaring it at the end of the day. So that denominator is always positive. If we take a look at the numerator now, if we plug in any x value where x is greater than 1, well, x is going to be positive. And the only thing that's going to cause this to be negative is that -2 in front. So this derivative is indeed less than 0 for all x greater than 1. So we've satisfied the second criteria in this case, that this function is also decreasing, in that the terms of the positive contributions to the series are decreasing themselves. So because our positive or strictly positive part of the series function satisfies those two criteria, by alternating series test, the series converges.